Example number 3 out of your textbook says that we are going to protect an antenna. And as soon as I get the thing to work. Alright, let's zoom in on it because we like to read. Okay, what's it say? It says that a small satellite dish is packaged in a cardboard cylinder for protection. The parabolic dish is 24 inches in diameter and 6 inches deep. And again, they made a little picture of it there. How tall must the cylinder be to fit the middle of the dish and be flush with the top of the dish? Solve algebraically. Alright, so let's draw a picture. First thing I want to do is establish what the size of the dish is. Is that example 2 or 3? That's 3, isn't it? Alright, so that's kind of what it looks like. And then your textbook went a little bit further and said that if you really think about it, this is the point negative 12, 6, and then equidistance from that is 12, 6. And so really that's kind of what it would look like graphically. And so we need to construct a cylinder that will hold it that's 6 inches by 24. Okay? And I'm not quite sure I understand the question, so I'm going to read it again. It says, how tall must the cylinder be to fit the dish and be flush with the top of the dish? So the diagram here that I drew shows the cross-sectional fit of the box itself. Alright, so what they're really saying is it has a cardboard cylinder for protection. So the dish goes inside this box. And what they really want is they want to build like a cylinder that's made out of cardboard. And that cylinder is going to protect the dish from having any type of damage, okay? So this is actually what they're interested in. How big does this need to be? Okay. So how do you figure that out? How do you make a cylinder? And the cylinder is based on the radius, right? So what would the height of the cylinder be and stuff like that? So one thing that they suggested is, look, this is parabolic, all right? So since it's parabolic, we know that we could represent this curve by y is equal to some variation of x squared. Now, since it goes through the origin, we just learned that last section about transformations, shifting left and right, moving up and down. Really, we're not moving left, we're not moving right because it's reflected across the y-axis and the vertex of the parent function is at the origin. So really what we're changing is shifting it horizontally, not shifting it, but stretching it or shrinking it. We don't know what that number is, but we're multiplying the function by a constant. Okay? So now how can we find that? Well, we know what x and y are. In other words, when y is 12, x is 6. So if I plug in my x and my y, I could solve for k, right? So if I do that, I end up with 12 divided by 36 is equal to k, or k is equal to 1 over 3, right? Wait, did I write that down right? Oh, you know what? I wrote it down backwards. You guys got to pay attention. This is x, this is y. So it's really 6 is equal to k times 12 squared, right? So I've really got 6 over 144 is equal to k, or k reduces down to 1 over 24. So that means that this curve can be represented by the function 1 over 24x squared. Does that make sense? And so now to verify those results, to make sure that Mr. Adams did it properly, because moving on from this point really doesn't help us much, I'm going to come in here and I'm going to graph this. So I go and I clear this out, and I'm just going to say 1 divided by 24 times x squared, right? Is that right? And then I'm going to set my window from -6 to 6. And we know, or no, -12. Why do I keep doing that? I keep switching my x and y's around. To +12, and then what do we know about the y minimum? 0. What's the y maximum in this case? 6. So we'll go a little bit above that, 7. And we hit graph. And so that's what we're looking at, roughly. Okay? So now, to find the cardboard cylinder, we need to find the height of the cardboard cylinder, which is really the diameter of the cylinder. What's the maximum height that this could be? 6. Is that the x or the y value? Alright. Were there any other parameters that they gave us? So I guess what we're trying to do is we're trying to find the cylinder that would fit somewhere in here and here, right? Would you want that cylinder to be symmetrical across the y-axis? Equidistant? Now what do you think would be a good place to place that cardboard box? In other words, if I were to think of an x value, where would you want to place that? Keep in mind that this is all the way over here. This is x equals 12. And this is x equals -12. 6? The truth is you could arbitrarily choose. So let's just choose 6. So what would be this point right here? What would be the height right here? In other words, if I put that there, how do I calculate the distance from here to here? Well, the first thing I need to know is how high this point right here is. So how do I figure out what this point right here is? Well, I could just plug it in my calculator, can't I? Trace, when x equals 6, what's y equal? 1.5. So this point right here is 6, 1.5. Now what does that mean? Well, what it means is if this total thing is 6 inches, in other words, from here to here is 6 inches, and this point right here is, from here to here is 1.5 inches, then what's the remaining thing? How do I figure that out? Well, if I say 6 minus 1.5, what do I get? 4.5. So now if I look at that and that's a cylinder, what I'm saying is that my diameter of the cylinder should be 4.5, right? Now what's the height of the cylinder? What does the height of the cylinder need to be? Well, we went 6 units this way. We should probably go 6 units this way. So what's the total height? 12. Thank you. So now, could I make the cylinder? Do I have enough information to manufacture those cylinders, and could I feel comfortable putting those in the boxes? Yeah. And it's rather easy to do, right? It should automatically put the pressure right here and keep the curvature of the satellite and protect it. Any questions on that?